Welcome to today's webinar. The topic today is fire resistance design of timber structures in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the content of the website, the German and English webinars, newsletters, customer projects, and so on. I will be the moderator today and I will answer questions together with Bastian Kuhn. The presentation will be done by Gerhard Rehm. Gerhard and Bastian are the main responsible persons for the development of the add-on timber design, and we are working also in the customer support. Okay, then I say some words how you can ask questions. Before I do that, I switch off my webcam that you can see the full screen. You can click on that question mark above. Then you can enter your question here, press send, and then we will receive your question and we will answer you. Okay, that should be all from my side. I hand over to Gerhard Rehm. Gerhard, it's your turn.
Okay, thank you, Andreas, for the introduction. The content of today's webinar is displayed here on the slide. We have a huge part today because of theory. We talk about the analysis method in case of fire design for timber structures. Mostly this part is really weak in our other webinars. But today I thought about to spend a bigger focus on the theory. We will not model anything today. We will switch to the program and I will show you the settings directly in the program. But the main focus today is the theory, that you will understand what is the background of the Eurocode, how does everything works with the charring and with the design afterwards. So we start with theory, then we switch over into the program, we check a few members, we check the design of surfaces, and at the end we will design cross-laminated timber for fire design. Okay. So the first topic today is about the general requirements. So this content here comes from the Bavarian building regulations, and I am sure it is similar in your country. It does not make sense to have a more detailed look into any regulations because we have so many people here from so many countries and every country is a bit different. But I guess in general this sentence says everything, so that's why I read it. Buildings must be arranged, constructed, modified and maintained in such a way that the outbreak of fire and the spread of fire and smoke are prevented, and that in the event of fire the rescue of people and animals and effective firefighting operations are possible. And I guess this is clear to everyone, that this is our big aim. Okay, so then we need to talk about stages of fire. So the first stage is the non-flaming smoldering before it goes over to the developing fire stage. Then we get the flashover where we receive the fully developed fire before it comes to the decay stage. And of course, when we think about this red curve here, you can imagine that this is hard to simulate in a structural analysis. That's why we need a simplification. And how this simplification looks like, you will see in the next slide. It's the content of the Eurocode 1, of course not the whole content, but the important content. It's about nominal temperature time curves. Here we see the standard temperature time curve. There are a few more temperature time curves, but for timber and especially for buildings, only the standard temperature time curve is from interest. That's why it's only listed. Yeah, we see this equation of the time curve. It's logarithmic function, and the variable is t. Next slide is about thermal decomposition of wood. I guess it's clear to everyone that in the beginning the wood begins to dry. So this is up to 100 degrees Celsius. From 150 degrees Celsius, the decomposition process begins. So we are around here. And it has its peak at around 270 degrees Celsius, where the cellulose decomposes and the formation of a char layer begins. And this char layer plays an important role, and it's actually the key for our timber design. That's why it's in bold letters. A few properties of this char layer. This char layer has a lower thermal conductivity than unburned wood. That's why it delays the charring, and hopefully a residual cross-section remains. And that's the reason why we have a very favorable behavior during fire in case of timber. As you see here, when you check the cross-section after a few minutes, I don't know how many minutes these are, maybe 30 or 60, you will see that the timber inside is brand new. It's still brand new. Fire resistance classes. So I don't want to spend so much time on it, since I guess that's clear to everyone. We have these classifications. We have load-bearing components and non-load-bearing components, but of course we are focusing, on the load-bearing components in our structural analysis. And we need to consider integrity or not. That depends on, of course, the building code or whatever. In the new Eurocode, this plays a more important role, and also we are focusing on it in the future, but for now we have no integrity. Or we do not prove any integrity, since it is actually not a design check like in terms of structural analysis, but as I mentioned, it becomes a more important role in the new Eurocode. And fire retardant, highly fire retardant, fire resistant. I guess that's clear to everyone. We talk about R30, R60, or R90, or R120, and so on. The indexes here are described on the next slides. I don't want to spend much time here. Please check the video afterwards and pause it. You will be able to read it in detail, what we're talking about. Today we're focusing only on the load-bearing capacity. Okay, so now let's start actually with the structural analysis part. Combination rules for actions. So we need to know which loads we can or we have to consider in case of fire design. In this case, we have to look into Eurocode 1, which refers to Eurocode 0, chapter 6433. And this is nothing else than the extraordinary design situations. There's a small error here. Sorry, it should be or and not the German word oder. I'm sorry for that. I forgot to replace it. So it's without any partial safety factors. You see it here, not for the dead load and also not for the variable loads. And there's only the question if you have to use C1 or C2 for the leading variable action. but this information you should become from the respective national annex of your country. Okay, so there's also this simplification where you use the internal forces or the actions from the normal temperature design multiplied by some factor, and you can design with this internal forces, but I do not recommend to use this simplification since it is mostly much way too uneconomic. All right. Next slide is about strength and stiffness as in case of fire. I guess you know this characteristic strengths Fk, Fmk or Fck and so on, Ftk. And this value is actually the 5% quantile value. In case of fire, we can use the 20% quantile value. So that means 20% of the values are lower and 80% of the values are higher than the characteristic values. Fortunately, there is no additional value in the material standards. Fortunately, they used this conversion factor K fire, which helps us to keep this database as small as possible. And you see the 20% quantile value is dependent on the material. It depends on the scatter of the material properties because it varies greatly compared from solid timber to glue lamp, for example. And I guess it's clear that the properties scatter because of branches and whatever, cracks. Okay, that's it. Let's have a look on this residual cross-section. Of course, when we check it here, when we check again this picture, we see the residual cross-section, but the question is only how we get this, effective cross-section. And the Eurocode 5 fortunately provides us charring rates for timber materials. And it's clear that a residual cross-section should remain, otherwise the whole design would not work or the whole building will not will collapse. And the question is only how this residual cross-section is defined, and it's simply defined by the cross-section where the temperature or the area where the temperature does not exceed 300 degrees Celsius. Then we need to talk about charring rates. We have two types of charring rates. So we have the one-dimensional charring rate, beta 0, which is used for surfaces in terms of RFEM. And we have the notional design charring rate, beta n, which is actually for members. Let's have a look on table 3.1 according to Eurocode 5. Here you will find the information about the charring rate beta 0 and beta n. For glue lamp, for example, it's 0.65 and beta n is 0.7. All right, so and the difference here, or actually the ratio, you can see is much higher for solid timber than for glue lamp. And of course, the reason is because solid timber has a much rough surface, or also cracks plays an important role, and that's why this ratio is much higher than for glue lamp. So the one-dimensional charring rate or charring depth can be calculated by multiplying the charring rate by the time. Also for the nominal or the notional charring rate, we multiply the charring rate beta by the time. And you see it's all about these corners here. When there is a fire, of course, there is no perfect sharp corner. You always have these roundings. Of course, it is hard to consider these roundings, or what means hard, it is time consuming to consider these roundings for timber design. That's why they have simplified it, yeah, and that's why we have this beta 0 and beta n charring rate. Okay, then we need to talk about design methods. And the Eurocode 5 provides us two different design methods: the reduced cross-section method or the reduced properties method. Both are described in chapter 4.2. Of course, both have advantages and disadvantages. So the advantage of the cross-section, of the reduced cross-section method, is it's applicable for any cross-sectional shape and material. And the disadvantages is this method is a bit less economical than the reduced properties method, which is the advantage, of course, of the reduced properties method, that it's more economical. But it has an disadvantage, of course. It's only valid for circular softwood materials and also only for rectangular cross sections for 3- or 4-sided charring of softwood as well. In our software, or actually the reduced section method can be used only when we talk about surface design. Yeah, for example, for CLT, the reduced section method needs to be used. In our program, we consider only the reduced cross-section method, but maybe in the future, I'm thinking about maybe to also introduce the reduced properties method, since the amount of work is not so high. So I'm thinking about to also overtake the reduced properties method for the member design. Okay, let's have a detailed look on the different design methods. Here we see the reduced cross-section method. Of course, we have the initial surface of the member, and it's getting reduced to the residual cross-section by the charring rate multiplied by the time, which we have here. And since the area between the green and the yellow line here has also an increased temperature already, and therefore a reduced strength and reduced stiffness, this area should also be neglected. And that's why we add some additional in times of, or for times higher than the 20 minutes, the factor key 0 is 1 and D0 is 7 millimeters. So we add additional 7, additionally we add 7 millimeters to our charring depth. Yeah. When we go to the strengths, we have a K-mod fire design, K-mod fire factor, but do not, interchange it by the K-mod factor from the cold state design, where we have, the K-mod factor dependent on the load duration class. In case of fire, the K-mod fire factor is always, or for this reduced cross-section method, the K-mod fire factor is always 1.0. And also the partial safety factor, since it is an extraordinary design situation, it's also 1.0. And therefore, at least at the global Eurocode, maybe there might be some national annexes, I didn't check it, which has higher partial safety factors, but I don't think so. And then you see this is 1, this is 1, and therefore the design strength equals the 20% quintile values. Okay, and also for the stiffness. Okay. The reduced properties method is actually similar. We have the initial surface of the member and we have the border of the residual cross-section. What we don't have is we do not have this additional 7 millimeters. So the yellow line here. That means the effective is the charring depths. But we have to consider a K-mod factor which is smaller than 1.0. And this K-mod factor depends on the perimeter of the fire exposed residual cross-section and the area. And this depends on the different strengths for bending, compression, tension, and that's why maybe makes it a bit harder for us, since we have to always fulfill a global we have to fulfill, how can I say it, the global design for all design checks. So there is nothing listed for shear, and there's nothing listed for compression perpendicular to the grain. So maybe we need to find a solution to also introduce this reduced properties method, and I have already ideas for it. Okay, that's it. Let's do a small example for this ceiling beam, which is softwood C24, 140 by 240 millimeters. Fire resistance period should be R30, and the charring should be at 3 sides, left, right side, and the bottom side. Okay, so what we do is we calculate our charring depth, multiplying the beta n factor from table 3.1. It's this table. Solid timber, which is C24. We have 0.8. And multiplied by the time, in this case, it's R30, means 30 minutes. We get 24 millimeters. And we additionally add 1.0 by 7 millimeters. And then we get an effective charring depth of 31 millimeters. Okay, now we take the 31 millimeters 2 times and reduce it. And we get 78 millimeters for the width and also for the height. 240 millimeters minus 1 times 31 millimeters equals 209 millimeters. Actually, it's really simple. Okay, then let's switch over to RFEM. So I'm sorry, maybe I should I'm sorry. I have loaded the wrong files. Because they were already finished, and of course I want to start directly when our ULS and SLS design is fulfilled. So we see this floor here. I have showed this floor with different variants in another webinar, I guess a year ago or something. You will find this webinar also on our website. And now, of course, I want to extend it for fire design. And what we will do is we will add an additional design situation, because we need our actions in case of fire. Okay, so I added the design situations here, and I will add another design situation. In this case, I select accidental fire. Watch out, there is also accidental without fire, but this should be used for example, an impact load or something. In case of fire, please use this one here. It depends on the national annex. Since we have only imposed loads and I use the German annex, I will use C2 in this case. Okay, and then we get our load combinations for ULS, cold state, and also the fire state, where we have imposed loads, dead load, and imposed loads on different spans. Okay. Of course, timber design results needs to be deleted. We want to add fire design here. All right, let's have a look on the floor beams. In this case, fire resistance config was automatically assigned to it. So in case you don't receive any results for fire design, please check if a fire resistance configuration was defined here. Let's have a look on it. Okay, so there are different tabs for members, surfaces, and some standard parameters. So in this case, it's exposed to fire on 3 sides, so not the top side. And we check it against 30 minutes. And when we switch to standard parameters, you will see all these beta factors for different wood and for different timber material. Okay, And you are able to change these values in case of some special settings from some special approval or something. Okay, so that's actually it. So here we can also check which fire resistance config is assigned. So in this case, this config 1 is assigned to all members and all member sets. Of course, if some member has a different setting, you can simply switch it here in this design configuration tab. And here you can also create new configs. Okay, so that's it, I guess. For now, I will run the analysis. And then we will check and compare, because the floor beams here, the ceiling beams, have exactly the same section like my hand calculation. So we had 78 by 209 millimeters. Okay, so let's focus on, it does not matter. We don't take care of the numbers for this example. Let's check this member here. And we check fire resistance. Let's check bending. And let's have a look at it. So it's not so, so interesting. We only see how the characteristic value is transferred into the, 20% quantile value. So we increase the strength, the characteristic one, by factor 1.25. So that's, okay, it's okay. And mod fire is 1.0, and also the partial safety fire factor is 1.0. Here we get the information about the fire resistance. So we have a T required of 30 minutes, and we have beta N of 0.8 millimeter for this material, multiplied by 30 minutes equals 24 millimeters. We add additionally the 7 millimeters, and we get an effective charring depth of 31 millimeters and an effective section of 78 by 209 millimeter, which was exactly the same value like in our example here. Okay. Let's go directly to the next example. It was this one with surfaces. So there's a small additional building next to another building, but the other building was not modeled. So that's why I have this fixed support here on this side. There is a line hinge here on this side, and there is a support here on the wall on the bottom side. So this floor here was made of an 80 millimeter glue lamp floor. So it's an orthotropic material model. So let's have a quick look on it. So I've switched to orthotropic linear elastic surfaces, where we have a different modulus in X and Y direction. Of course, this is made of multiple pieces of glue lamp. So maybe 80 by 625 millimeters or 620 millimeters or something. And of course, there should be no moment transfer in Y direction of the surface, but since we span it directly in one direction, there is no big difference. Of course, if there is another support here, then maybe we should think about to reduce the stiffness in Y direction or add some line hinges, but for this example, it's absolutely okay. Okay, so what I have done here was I have defined some fire config for surfaces. So we check it. Let's check it against 90 minutes. To make some extreme example, you can imagine we have 80 millimeters and we expose it to fire for 90 minutes. Yeah, you can imagine what happens. And we want to have the sides or the fire only exposed on the bottom side. So that's all what we enter for now. We come to all other settings later. Okay. So we need also this design situation. I will add a new one here. So in this case, I select this one because wind is also considered here. So we have that load, we have snow load and wind load, and we have a really, a high dead load because I have to find 2.5 kilonewton for load case 1 in this example. Okay, let's check it. Yeah, we have load case 1, load case 2, which is snow, load case 3, which is wind, and load case 4, which is also wind. Yeah, as I mentioned for the German annex, this load combination can be neglected, but for now I'll leave it. Okay, so that's actually all. Oh, sorry, I forgot to create it. A minute. I hit the cancel button and not the OK button. That's why it was not saved. Yeah, let's use the first one. Okay. Yeah, that's actually all. We focus only on the floor for now. I start the analysis. And then let's check what happens. Yeah, so you maybe have a focus on this diagram here. You see already, yeah, the deformation becomes extremely high. So we are around 1 meter 30, 1 meter 40 deformation. Yeah, and you see there are some errors, but fortunately we get some results. But of course, when we check the deformation for this load case, yeah, the maximum deformation is 1 meter 60. The span of the floor has only 3 meters, so it's 50% of the span length. And I guess that's clear that no firefighter will enter this room when he sees that the floor will deform like this. So yeah, but at least we get results. But watch out, it can happen when you don't take care of it. Of course, it's clear nobody would apply 90 minutes to a 80 millimeter panel. So it can happen that the structure becomes unstable, especially when we talk about P delta analysis, so second order effects. Yeah. Then of course the critical load factor plays an important role, and of course the structure becomes unstable under some circumstances. This needs to be considered. Okay, so in this case, it's clear this floor will definitely not work. And when we check the ratios here, you see directly, okay, the ratio is extremely high. Let's check it directly. We will see, okay, we have the jarring depth here calculated, and the remaining thickness of the surface is 14.5 millimeters. You can enter and see each intermediate value here in this dialog. But there's also this diagram here on top, or also when you close it and click here. And then you will see, let's switch to the stresses. You will see, okay, we had the 80 millimeter and the remaining thickness, the effective thickness is only 14.5 millimeters, which is of course too low. And the jarring depth here can be seen by 65.5 millimeters. And now it's the question how we can fix this. Of course, we can increase here the thickness of the surface, but there is another way what we can consider. So let's go back to our PowerPoint. And now we talk about initially protected components. As you can see, this is, I guess, the most common case to cover it by some gypsum boards. Yeah. The advantage in this case is we save time. Yeah, because the gypsum boards in this case, or all other claddings, yeah, they causes a delay. Yeah, so the timber will start to burn much later than without this cladding. Of course, it depends always on if the quality of the timber should be visible or not visible. That's clear, but in case it's not visible, then yeah, we can apply such claddings. The Eurocode describes different stages of or different stages or phases of fire, and we will have a look on it in detail now. Okay, maybe you have seen similar diagrams like this. So let's have a look on this diagram. So curve 1 is the charring rate for the unprotected surface. So that means we have a linear charring rate. It's nothing else than, actually in this case here, that's the charring depth. It's nothing else than beta 0 multiplied by the time, and of course it is linear. Okay, and of course the timber starts to burn exactly at t equals 0. And now we come to this delay, yeah, when we use some protection. And here we see two different curves. So we see curve 2 and curve 3. We will talk about both curves in detail on the next slides. Here you see the time of the delay of charring to protection equals the failure time of protection. That means the protection will fall down from the floor, for example. At the same time, the fire starts, yeah, on the timber. And the second curve is the protection is still active. It's still on the floor, for example, but behind the protection there is already the fire behind the protection has started already, yeah, but the protection is still on the floor. So in this case we can consider a reduced charring rate until it will fail. Yeah, and after the protection is gone, we will have some increased charring rate again. You see here we have this 25 millimeters limit, and after this 25 millimeters, the normal charring rate will continue. Yeah, and that's the time TA, and this time, or this T is actually the time in minutes from which a char layer with a thickness of 25 millimeter is present, and yeah, no increase in the burn rate needs to be applied anymore. Okay, let's have a look on it in detail. Okay, so for wood-based panels, gypsum plasterboards type A and H, we can use this curve number 2, where the charring equals the failing time of the protection. Yeah, for wood, it's simple. We can simply divide the panel thickness by the charring rate, and then we know the time. Yeah, for the, I guess, most common case using gypsum plasterboards, we have equations in the Eurocode for fill joints or gaps smaller than 2 millimeters, or for gaps higher than 2 millimeters. So for a typical 12.5 millimeter plasterboard, yeah, the charring time here is 21 millimeters. So the delay, the fire will start 20 minutes later. Yeah. So, but as you can see here, we have an increased charring rate afterwards. So at the end, I guess this was, I'm not sure, it was 60 minutes. At the end, with this time, we don't save much time, because here we can consider a linear curve, and here it's bilinear. So we have an increased charring rate here. You see here the charring depths for part 2A, and here we see this factor K3, which is 2. And the reason why we have to consider an increased charring depth is nothing else than the temperature. yeah, next behind the protection is already really high, and of course the timber dries out, yeah. So, and of course the dry timber is burning much faster than wet timber. That's clear, I guess. And that's why we have to consider this increasing charring rate. And the time where this char layer becomes its 25 millimeters can be also calculated by this equation, which is also listed in the standard in the Eurocode 5 part 1.2. Okay, so we need this time, and we know this time, TA and T charring, and therefore we can calculate our charring depth by adding charring depths 2A plus 2B. Okay, so what we also need to consider, there is also a minimum penetration length because of the fasteners. So in case T charring equals TF, we have to add 10 millimeters to the to the protection thickness. That's clear because we don't have to add any charring depths here in this equation because the timber is not burning, yeah, at this time. It is different here when TF becomes higher than T charring. That's the case for gypsum plasterboards type F and gypsum fiberboards. Same equation like for the other slides, so I don't spend time on this. But yeah, the big unknown is this time here. So the time of the failure of the protection. And Eurocode 5 does not say anything about it. Okay, it says something in Annex C, yeah, to get the values from tests. Of course, this will not help us engineers. So in this case, we have to look in other approvals or in other codes. For example, the ÖNorm from Austria, they provide values for type F. Yeah. So in this case, for one layer, yeah, it's 2.2 by, for example, 12.5 millimeters plus 4 equals 31.5 minutes. So compared to 21, we will have an additional reduced charring rate for additional 31.5 minus 21 minutes. Or maybe also in the new Eurocode generation, there will be values for it. In this case, this equation results in 32.5 minutes. Yeah, it's a minute longer than the ÖNorm approach, but at least we get some values. Okay, or also have a look on the approval. For example, here at Stora Enso, they provide values for 55 minutes, so 20 minutes longer or more than 20 minutes longer than the other approaches. So this will help you, of course, a lot. But of course, the gravity takes an important role, and therefore there's to distinguish between walls and floors. Yeah, let's have a detailed look. There's also this equation about the about the 25 millimeter of the char layer, and also the charring depths for 3A, 3B, and 3C. Oh, sorry, there's a small mistake. It should be 3C. Yeah, K2 is the reduction factor for this part. For classical 12.5 millimeter gypsum board, it's 0.775. Yeah, then we increase the strength here again because of the temperature and the dried timber by factor 2. And here at 25 millimeters, we start again with a normal charring rate from table 3.1. And here, additionally, we have to add the charring depth at this time when the when the protection will fail. Okay. Yeah. Next slide is already about CLT. Let's switch back to our program. So we will go to the fire resistance configuration again and go to surfaces, and here I will activate the initial fire protection from bottom side. As you can see it, this is the default, or these are the default values. Default value here is 21 minutes, which is the result from 12.5 millimeter gypsum plasterboard. K2 value, it's 0.775. In this case, let's start with TF equal T's charring, and this increasing factor K3 should be considered with 2.0. So, okay, we need to recalculate everything. As you saw, also the internal forces and the results from the load combination for the accidental actions got deleted because we sent the reduced section to the solver. So all the stiffness is considered with a reduced stiffness for surfaces. Okay, when we run the analysis again, before we had a effective section of 14.5 or 14.8 millimeter, deformation was at 1.60 meters. Now we get a deformation of around 1.30 meters or 1 meter or something, a ratio of 280%, of course, still too high. Let's check the thickness. Okay, we won 1 or 1.5 millimeters, so not really much. Okay, let's go here to surfaces again, and maybe let's try the value from ENORM or from the global Eurocode. Let's switch to 31.5 millimeters. But sorry, my mistake. It was for the walls. In this case, we should consider here the floor. In this case, maybe better to use 2-layered. So this is this cell here. It's 1.4 multiplied by 2 by 12.5 millimeters plus 4. Becomes 39 minutes. Okay, so maybe better directly to use 39 minutes here. And then let's see how far we can go, and maybe we come close to the 100% ratio. Okay, the deformation is at 30 centimeters, which is not too bad in case of fire, and the ratio is close to 100%, so it's 1.31. Since we have already 2 layers of gypsum board on it, maybe it's worth to think about to increase the thickness of timber bit. In this case, maybe, or I'm nearly sure 100 millimeter, the increase of 100 millimeter glulam will be enough in this example. But okay, that's okay for now. Time is running quick. Maybe switch over directly to the slides and have a look on CLT, which has some special rules. Before I start with CLT, as you know, it's not directly regulated in the global Eurocode, in the current Eurocode. It is covered in a few annexes like the German and the Austrian one, but this timber design is not part of any annex. So this is actually the current state of the technique, and it will be also part of the new Eurocode, and it is also already in some approvals from producers. So for example, Stora Enso, they use this approach, and also a few others. Okay, so first we talk about linear charring. That's nothing else than our solid timber. So same rules. The only additional rule is for CLT and linear charring, layers smaller than 3 millimeters should not be considered anymore in the design, because the charring is of course not perfect symmetric over the whole surface, and that's why it's better to neglect layer thicknesses smaller than 3 millimeters. And the linear charring can be used only for heat-proof adhesive. Mostly this is not the case for CLT, so I don't know any producer. Maybe there are producers which uses heat-proof adhesive, but it is more common to use non-heat adhesive, like the polyurethane adhesives. In this case, we need to consider a non-linear charring, because the temperature influence on adhesive causes delamination. Yeah. Let's have a look on this image here. You will see this is a CLT floor. You see the longitudinal layers and the transversal layers here. And yeah, you see this coal or this char layer, which helps us actually to reduce the fire, is completely gone within a second. Yeah, it is there, then it falls down, and then there is no protection. And yeah, the timber is the temperature in the timber is really high. It's really dry, and you can imagine there is additional increase in charring rate. Yeah, in similar actually to the initial protected components. There we use the same approach, and you will see on the next slide. This is this stair model, sometimes called, where we have different areas as well. So the first area is here A. Here we consider a normal charring rate with beta 0. The most approvals use 0.65 millimeters per minute, but other approvals, maybe they use 0.7. It depends always on the approvals. Yeah, so the first area is 0.65 millimeters, for example, per minute. And then we come to the second layer. So let's assume, okay, the layer falls down. So the timber behind is already threatened with a high temperature. That means we get an additional increased charring rate. In this case, we call it K beta. So it's also factor 2, similar to the initial. Let's switch to this slide, to this one, yeah, to this initial protected components. And here we go. Then when the char layer actually reaches 25 millimeters, we can continue with the normal charring rate, and then it starts from the scratch. So from here again. And so on, and so on. But of course, this is 120 millimeters, and you see for 0.65 millimeters, we get an effective thickness, or we get an charring depth, an effective charring depth of around, let's say 110 millimeters or something. Yeah, let's have a look on it in detail afterward. Okay, also the 3 millimeters should not be taken into account. Yeah, and this is for roofs and ceilings. For walls, of course, here the gravity plays an important role. I guess that's clear. For walls, yeah, gravity plays a role when it falls to the side, for example. Here we also have a bilinear curve, but we do not have such a high increased charring rate. So the first layer will be burned by 0.65 millimeters per minute, for example, and the second and all following layers becomes a charring rate of 0.86 millimeters per minute. Yeah, in a few approvals, this value here and also in literature is recommended to use. Also 3 millimeters should not be taken into account. That's clear. Let's have a look into the program again. So I will replace this layer by layer number 2. I have prepared it already. It's a 5-layered Stora Enso composition with 30, 20, 20, 20, 30 millimeters. The span direction can be checked here with these blue arrows. You will find them in the display navigator, surfaces, layer direction, and I display the resultant. Of course, you are able to also add per layer and with indices, and then you will see directly about the layer direction. But for this example, I prefer to see the resultant stiffness direction. Okay, maybe let's leave also the settings directly like we had before. Yeah, we can leave it and run the analysis again. And let's see the differences between the CLT and the softwood or solid timber. Okay, deformation was not really high. It was around 120 millimeter. Let's have a look on the ratios. Let's check the ratios for, let's say, higher than 20%, and we get a smarter overview about ULS design is 20%, SLS around 31%, and fire design, yeah, will control in this case with a ratio of 79%. And let's have a look on it in detail. So we check the charring depths and we get the information directly. Okay, layer number 5 fails, number 4 fails, layer number 3 fails, and layer number 2 will be reduced to 12.6 millimeters. Of course, it's much easier and much nicer to see the effective section here in this dialog. Maybe we switch to stresses again. Yeah, you will see 77.4 millimeters will fail, and 30 millimeters on top, of course, will remain, and on the second layer, 12.6 millimeter will remain. But of course, since this is the transversal layer, this layer is not able to support the first layer. That's why the stresses are only considered on the top layer. Yeah, and this helps us, of course, a lot to understand the effective section. But of course, I agree. Yeah, the charring rate, to check the charring rate inside the tables, it's sometimes a bit tricky. And when, of course, you can check each value, each intermediate value, that's clear. But of course, it would be much smarter to see it graphically. And that's why we have introduced, or we are introducing now, will be finished in a few weeks, this time course monitor, where you can see the charring depth over the time. And this helps you, yeah, a lot to understand and compare it with my slides in the PowerPoint presentation. So for example, here on the right side, that's a floor, and we see here the border of the residual cross section, and we add, of course, the 7 millimeters here. That's covered by this red line. So we have a protection, you can see here, because the burning starts at 21 minutes in this example. And yeah, then we have the double charring rate, then we reach the 25 millimeter limit, then we have the normal charring rate again, and then from the beginning, double charring rate until we reach the 40 plus 25 equals 65 millimeters, and then we continue with the normal one again. On the left side, we see a wall. Here on this side, it's not covered with the protection. on the bottom side, we see a protection. So it starts at time 0, and yeah, the charring rate or the charring depths increase for the first layer linearly by this charring rate of 0.65 millimeters. And from the second layer on, we get this increased charring rate. On the bottom side, we see, okay, a protection, and here it's the same. Yeah, we start with an increased charring rate until we reach the first or the second layer, and then we continue with this 0.86 millimeter or whatever you have defined in the fire design config. So here you will see for cross-laminated timber, and dependent on if you have heat-proof adhesive or non-heat-proof. Oh, I forgot to show you. Here in this surface dialog, you will find the distinction between wall and ceiling. When you select ceiling, then this approach here will be used. And when you select wall, this approach will be used. Of course, the program does not know if this is a wall or a floor. This needs to be a user input. And yeah, dependent on the setting here, you will get this. Settings. You can also define the thickness, the limit of 3 millimeters. When you want to consider it, of course, you can enter 0 here or a higher value. And also there's the option to define a user-defined coefficient of layer thickness with 0 strength. So of course it's 1.0.7 in the most cases. If you want to consider higher factors, you can use it here. All right. Yeah, that's it for the floor. And yeah, time is already over, but I will show you the wall configuration. So you need to create a new fire config. So I create a new one. For surfaces, you can switch over to wall in this case. Yeah, define your required time and your settings. If it's exposed on top or bottom side, top is always -C direction and bottom is always +C direction. So when you right click on the surface, you can activate the local access systems here, and then you see, okay, plus is in plus direction and minus is in minus direction. Yeah, and don't forget to, wait a minute, I forgot it. I will switch over to wall, or I can, maybe I don't want to create a new one. I want to create a copy, and I will switch to wall. Okay, and now I have assigned the wall config, yeah, to my wall. Okay, so for now, that's it from my side. I'm thinking about to do another webinar on this, especially when we talk about wall design, especially when we talk about backlink design of CLT. We had already a webinar about backlink design of CLT in RFEM 5, which can be overtaken actually to RFEM 6. But yeah, maybe in the future, I plan to do a webinar where I show also, yeah, the eccentric effects and the backlink effects on this walls, for example. Okay, yeah, so as you saw, it was really focused on this PowerPoint, but yeah, I was focused on all this information to provide also to following users to watch the webinars and yeah, to learn about this fire resistance. This helps the user, of course, 24/7, and of course this helps us in the hotline where we don't have to answer the questions, because of course you yeah, can check it out in this webinar. And hopefully I fulfilled your expectations, and yeah, that's it for now. Hopefully I did not forget anything. Oh, maybe, yeah, some words on literature recommendations. Unfortunately, I'm not familiar with some English literature, so I know only the German ones because the German ones are already really good. I'm sure there are English literatures, but yeah, I have no clue about. Yeah, maybe you can send me some English literature sources, and then I can add it to this PowerPoint later. Okay. Then I want to thank you for your time, and yeah, see you soon, hopefully. I will hand over to Andreas again. Thank you and goodbye.
Thank you, Gerhard, for this nice presentation. An additional hint from my side, just book your free online appointment, such as a product demonstration of our main programs, RFEM, RSTAP, our Wind, our section, or yeah, a demonstration of our add-ons, or of one or two or more of our add-ons. Just contact our sales team by clicking that link here, or you can scan the QR code. You will find the presentation slides on the same website where you can find the recording. And the next days you will get an email with a link to the website with the recording and the slides. Okay, it should be also all from my side. Thank you for your attention. Thanks to Gerhard for this presentation. Thanks to Bastian for his support by answering the questions. I hope we meet each other in a future webinar. Yeah, have a nice rest of the day. Bye bye.